Alright, our final effect to consider when it comes to SN2 reactions is the role that solvent plays. So first thing we can say is that most of these reactions require polar solvents. And that's because, as you've seen with the examples we've looked at so far, in many cases we're dealing with ions or highly polar species. And so if we try to use a nonpolar solvent, basically things won't dissolve. And if things don't dissolve, don't go into solution, we don't get a reaction. Now we're going to divide our solvents up into protic and aprotic. And the difference is whether a solvent has an acidic hydrogen. So the common examples of protic solvents would be things like water, as well as alcohols. Both of these have protons that are at least somewhat acidic, and so we call them protic solvents. Aprotic solvents, and we'll show some examples in a few minutes, do not have an acidic hydrogen. And so acetone might be an example. Alright, so why the difference? And why do we distinguish between these? Well, protic solvents can do the following. So if we have a protic solvent and we have some sort of nucleophile, the hydrogens on that protic solvent coordinate to the nucleophiles. What does this do? What's the consequence of this? Well, this stabilizes the nucleophile. As a result of stabilizing the nucleophile, it lowers its ground state energy. So if you recall these types of graphs that you saw in general chemistry, where you plotted energy versus the reaction coordinate, for an SN2 reaction, these would look pretty simple. In many cases, SN2 reactions are exothermic, and so we get a nice simple plot that looks like this. But if we add a protic solvent, that protic solvent stabilizes the nucleophile. By stabilizing the nucleophile, it lowers its ground state energy. Now, in order for the reaction to take place, it's going to go through the same intermediate and get to the same product. So at some point, these two graphs will merge. But what's the big difference here? Well, for the original reaction, this is our activation energy. But when the nucleophile gets stabilized, we end up with a much larger activation energy. And so what happens by adding that protic solvent, you stabilize the nucleophile, the reaction does not occur as easily. So for an SN2 reaction, the preference is for polar aprotic solvents. what are some examples of these? Well, acetone is a good example. If you take Organic 2 lab with me, we very likely will be doing a lab where we compare SN1 and SN2 type reactions. And in that experiment, we use acetone for the trials where we want to favor SN2. CH3CN or acetonitrile is another common solvent that's good for SN2. The next one that I'm going to draw is actually one of the best solvents out there for SN2, but we don't use it anymore. This is known as HMPA, and you can see its structure here. So HMPA is hexamethyl phosphoramide, and as I said, it's one of the best solvents out there for SN2 reactions. But it has been found to be fairly, at least somewhat carcinogenic, and to the point that people don't really want to use it anymore. And so in many cases, instead, we use DMSO. But all four of these solvents have the common property of they're polar. We should be able to identify a polar bond in every one of them. Carbon-oxygen bond, the carbon-nitrogen bond, the phosphorus-oxygen bond, or the sulfur-oxygen bond. So they're all polar molecules. But in addition to that, none of them have any acidic hydrogens. And so that makes them ideal for an SN2 reaction. So we've now finished our 4 properties and our information on SN2 reactions. We'll continue in our next video by starting to look at SN1 reactions. And once we get through those, we'll compare the two of them and then get into some practice.